All right, last thing about waves is we're going to talk about different wave problems that you can see. I'm going to give you a couple other equations that might be beneficial, especially for the dual credit side, but they could be beneficial for all of you. So let's look at the first problem. Okay, so this one's more conceptual, but wave versus particle velocity. And the question is the velocity of a wave moving along a rope? Okay, so the wave that going this way, is it the same as the velocity of a particle on the rope? And when you look at this, the first thing you want to think about is velocity's distance over time for the particle. But when we talk about the wave, right, it's wavelength times frequency. And so we're talking about different things here when we talk about the speeds. So of course the answer is no, and because they're moving in different directions, but they're also measured differently. And I think that's the key, is that wavelength times frequency is the speed of the wave, but the amplitude is just distance divided by time. Okay. Here's a math example, and before we start, I want to give you an equation here. It's this one here that deals with tension, okay, on a string, on a wire, whatever. But the velocity is the square root of tension over mu. Now, mu is not coefficient of friction. Mu is something fictional. Not fictional, I guess. I mean, mu is mass over length, okay? So substitute that in for mu. And so the velocity of a string is going to be the square root of the tension over the quantity of the mass divided by length of the wire. So let's take a look here. A wave whose wavelength is 0.3 meters is traveling down a 300 meter long wire whose total mass is 15 kilograms. If the wire is under a tension of 1,000 newtons, what are the speed and frequency of this wave? Okay, so first thing we want to find, right, is speed. So speed is going to be the square root of tension, which is 1,000 newtons, over our mass, which is 15 kilograms, divided by the length of 0.3 meters. Okay, so you want to do the bottom part first mathematically. Then you're going to take 1,000 divided by that. Then you're going to take the square root. But you'll get a speed of 140 meters per second. So that's our wave speed. Okay, again, this equation is beneficial when we're talking about wires and tension and forces. Now that we know the speed of the waves, 140 meters per second, then what we want to look at is the frequency. Speed, wavelength times frequency, so it's going to be 140 divided by 0.3. I'm going to do that really quick here in my calculator, and I get 140 divided by 0.3. I get 467 hertz, and that's the frequency that it's a Z, the frequency that our wires vibrate. So we can find this vibration frequency. Again, important when we talk about stringed instruments. Another one is intensity of waves, and an equation about intensity and sound, or intensity of an earthquake, but it's going to be, when we look at intensity of a sound, it's in watts per meter squared, okay? And then R is just the distance away from the source, okay? So pick something to be I2. I'm going to pick 1.0 times 10 to the 6th to be my I2. I want to find the intensity at a different distance, so that's going to be my I1. Now this is where you got to be careful. R1 is the distance for I1, so that's 400 kilometers. And the distance of 2, which is the one above, is 100 kilometers. And now we just cross multiply. I1 then turns out to be, obviously, a higher number because it's closer to the source. And it's 6.3 times 10 to the 4th watts per meter squared. So if we see sound intensity or intensity of a wave, understand that the closer you are to the source, the more intense the wave's going to be. As it comes out, there's going to be damping. It's going to spread out farther. This intensity is going to go down, the power per meter squared. Okay? So just keep that in mind. All right, so now looking at frequencies, wavelengths, fundamentals, harmonics, all these things that we talked about in the other video. Here's length. Okay, so we got the length, so the length of our string will be the harmonic times the wavelength of that harmonic divided by 2. If we want to find the wavelength, it's 2L over N, with N again being the harmonic string fixed at both ends. And then our frequency of our harmonic in this one is, if you just take the fundamental frequency, or the frequency of the first harmonic, and multiply by the number of harmonics, either 1, 2, 3, etc., you can find then the frequency at that harmonic. Equations that might come up at some point on the AP test, or I put it on, I'm sure it's on the homework somewhere, but on the AP test you might see something like this. Again, these are just shortcuts to be helpful. So here's a use. We got a piano string with a 1.10 meter long, has a mass of 9 grams. We want to know how much tension must the string be under if it is to vibrate at a fundamental frequency of 131 hertz. So we're kind of tuning our piano here. What are the frequencies of the first 4 harmonics? All right. So first off, the tension. Okay. So we want our first harmonic frequency to be 131. Now we want to find the other 4 after that. So the first step is to find the tension. And to do that, we have to know what our wavelength is. And this goes back to the equation that we talked about here, right? V is equal to the square root of Ft over m divided by L. So first off, we want to find the wavelength, and we can find the wavelength. It's 2L over N. Since we're talking about the fundamental frequency, that's N's 1. So the wavelength is 2L. So 2 times 1.1 is 2.2 meters. So now we know the wavelength that's coming out of our string. Wave speed is equal to wavelength times frequency. So we take this wavelength and multiply it by our 131 hertz, and we get 288 meters per second. So now we know our wave speed. Once we know all of this, now we can solve for tension. And here's that equation solving for tension, right? M over L times V squared. I want to substitute. Okay, when I substitute this, M over L is going to be 0.0009 over L, which is 1.10, right? That's our mass in is that right? Yeah, in kilograms, right? Should be I'm sorry, 1, 2, 3 should be 0.009 over 1.10 meters, and then we multiply that by 288 squared, and we get a tension of 679 newtons. So now we found our tension. So now what are the frequencies of the first 4 harmonics? Really, since the frequency is equal to n times our fundamental frequency we found to be 131. To find it for n equals 2, we just take 2 times 131, which is 262. For the third harmonic, it's 393. And for the fourth harmonic, it would be 524. And all of these are measured in hertz.